Welcome to the Cosmic Pie Podcast, episode 32.
32,
Season 3. I'm your host, Wayne Barkhouse.
And I'm Robert Moore. Oh, wow.
He forgot all of a sudden who he was. Where's your ID, Robert? Check the ID.
I forgot where I was this morning.
Pat, I'll tell you your name. Just hand me over your credit card. I'll read it off from there.
Okay.
Okay.
And the numbers?
1, 2, 3, 4, 5, 6. So we are broadcasting live here from the campus of the University of North Dakota in Grand Forks, North Dakota. You betcha.
You betcha.
Oofta.
Don't you know?
It is what it is. Got to get it all out in front at the beginning so we don't forget to say it.
Are we going to exchange recipes for hot dishes?
You know, summer finally...
Sorry, folks.
You know, summer arrived.
Summer?
Summer's here. Did you notice how hot it's been lately?
I did.
And very little rain
Of course,
had. So
what I notice is an astronomical phenomenon.
what's that?
And that is that it's still getting up and around 80 degrees during the middle of the day.
Yeah.
But have you noticed how sharply the temperature drops about an hour or two after?
Yeah, well, did you
noon?
notice that it gets dark quite rapidly as soon as the sun sets? So the angle, the trajectory that the sun takes when it's below the horizon is almost 90 degrees now.
Right.
And so it drops off dramatically.
So it's chilling at night pretty nicely, and it takes a little bit for it to warm up to that 80 degrees through the day. It's not like the summer where, it was 80 degrees pretty much as soon as the sun popped up.
And tomorrow's the 1st of October.
Right.
And I remember, you know how I remember? Because
How's
you can
it?
look back on Facebook to see a picture taken on October 2nd, our first snowfall of the year. And it's like, don't want that this year.
I don't think we're going to get that.
Let's wait till the 2nd of December. That would be more like be festive for the holiday season.
Yep.
That would be better. Anyways, we do have a live chat that's running, so if you have any comments or questions that you'd like to ask us throughout the podcast, feel free to use that feature.
Mm-hmm.
The other thing is, we do upload our videos the next day on Spotify. I noticed we got a few viewers on Spotify now.
Oh,
So
cool.
it's starting to spread a little bit. I
So
wish
our
it would.
fame is
I
spreading.
wish it would spread more like the COVID,
Right.
so then
right.
we could get attention of millions of people. But
Yeah.
it doesn't, and it hasn't. The other thing too is our disclaimer, Robert. If you
Yeah.
like it today.
Okay, yeah. The opinions and views expressed herein are those of myself and Wayne. They are not the University of North Dakota's opinions, nor the Department of Physics and Astrophysics. It's just us, folks. Just two guys,
Shooting the breeze.
shooting the breeze and talking about science. So.
Sign. You blinded me by.
Yep. Do-do-do-do-do-do-do.
You gonna sing for us now?
No.
Who was
That
the
might
person-
get us
who
in
sang
trouble for
that? It was,
copyright.
Dobie?
Thomas Dolby.
Dobie. Yeah, that would get you copyright.
Yes,
system
yes, it
probably,
would.
right? So we better not do that. Okay, so today we're going to go through a list of science items that have been in the news lately.
Okay.
So let's start with
Number one.
number 1. This paper you can see on the left side, it's the interaction of a couple of galaxies with the nearest galaxy cluster to us. Nearest, of course, is a subjective term here. It's
Astronomically speaking.
It's 65 million light years away, and this is the Virgo galaxy cluster. In fact, our Milky Way, along with dozens of other galaxies
Is
near
heading
us,
towards them.
is the local group, as we call it. It's on the outskirts of what we call the local supercluster. And at the heart of the local supercluster, at 65 million light years distant, is the Virgo galaxy cluster.
Cool.
And which constellation do you think the Virgo galaxy cluster is in?
Leo.
Close. At least you got a name of a constellation. You just
Right.
didn't make up some random thing. Right? So it's in the constellation Virgo, obviously. Now, 65 million light years, that is a long ways away. But in the nature of things, the size of the universe, that's in our backyard,
Right.
relatively speaking. So a good way to think about it is, traveling at the speed of light, it would take you 65 million years to reach the Virgo galaxy
The
cluster.
light that is reaching us now, there were dinosaurs still on Earth. So,
Well, it's about that time, isn't it?
yeah.
Now, light that we see from very distant galaxies, that's been traveling for, like 13 and a half or so billion
years.
So there's the difference in scale.
Right.
So light that leaves us from a distant galaxy on the other side of the observable universe, that left long before the Earth
Was
and the
formed.
sun or our rest of our solar system even formed.
Right.
It wasn't even an idea in God's eye. You see, not even a gleam or a
Not even a glimmer,
not even
a twinkle.
Twinkle in his eye. It was
Yep.
that long ago. Now, what's interesting about this research, if you like, are that these two galaxies, which are on the outskirts of the Virgo cluster, and we can see the optical image in the far right. The radial image is to the left of that, and the optical and the radial image are looking at the same region of space, but notice this brings up the issue of our biased view of the universe.
Mm-hmm.
If we looked in optical, so the far right image near the top, you see one galaxy sort of at the top and another one sort of at the bottom left. If I said, do you realize these two galaxies are like interacting with each other? There's a connection. You're like, no, they
I
don't.
would be laughing at you. And
Yeah, they look totally isolated right, from
Absolutely.
each other. But if you look in the radial image, which was taken by ASCAP, which sounds like it's a dirty thing. You have to
yeah, it
watch what you
does,
say
doesn't
here.
it?
It's by the Australian Square Kilometre Array Pathfinder. There's a whole story there in a second we'll talk about. It's measuring the hydrogen gas that's in the vicinity of these galaxies, and that's the image sort of in a brownish, reddish, yellowish type of colors that you see mixed together. And there's clearly a connecting bridge between these two galaxies of hydrogen
Mhm.
gas. And they're interacting with the outskirts of the Virgo cluster itself. So they're falling inwards, they're dragged in by gravity, because that's a high concentration of matter in the galaxy cluster itself. And as they come in, they'll interact with the environment of the cluster.
Right.
And one of the things, there's two things going on here. Number one is that they feel what's called the ram pressure stripping. So ram pressure is when you have hot gas and you run into it. It's almost like the snowplow effect type of thing.
Yeah.
And what will happen is it will tend to strip away, or at least at some amount of material from the galaxy that's falling in. The galaxy, through its gravity, is not able to hang on to all of the gas and dust that it contains. So
Mhm.
that some of that material can be torn away. And you get these rather peculiar looking galaxies. We call them jellyfish galaxies.
Oh, right. Yeah.
So they look like
jellyfish.
jelly beans. No, they look like jellyfish. The long tendrils,
Long tendrils
of gas
hanging
and
from
dust.
them, yeah.
Yeah, that's trailing the galaxy as it falls into a dense environment.
Right.
So there's these kind of effects that's occurring in the vicinity
Now,
then of this cluster.
I've got to get into some of the chemistry of this. H1, so this is neutral elemental hydrogen, correct?
Neutral atomic hydrogen.
Atomic, sorry.
Yeah.
Elemental atomic, yeah. So it's not molecular hydrogen and it's
No.
not ionized hydrogen.
That's correct.
Okay.
Yeah. So the good thing about the neutral atomic hydrogen is that there is a transition that occurs due to the hyperfine splitting of the ground state of the hydrogen atom. There's a mouthful.
Yeah.
What it means, if you go to the lowest energy level, there's not just a single level, like the bottom rung of a ladder, if you think of it that way. If you look carefully, there's actually two closely spaced energy levels. It's like if you looked at the bottom of a ladder and you see one rung, and then you put your glasses on, and there's like two of them really close together. They look like one when you couldn't see really well.
Right.
That's kind of what you see here. And what happens is when the electrons descend down the energy levels, they like to be at the lowest energy place. I mean, all of us like to be in the lowest energy
Yep.
state. That's why I can lay on my couch, sit back on the pillows and watch TV, because that, for me, that's a low energy state.
I think that's the low energy state for a lot of us.
And so the electrons, when they move down to the lowest energy state, they go into the upper level of the lowest energy state, but that's not technically the lowest energy possible. So they stay there for a while and then eventually transition to the lowest energy state possible.
Okay.
And when that occurs, they have to give off energy, and that energy is given off in the form of light, photons, particles of light. And in this case, since we know the energy difference between those two levels, we can calculate what is the wavelength of the photon, and it comes out to be 21.1 centimeters. Well, 21.1 centimeter photon is out in the radio.
Yep.
It's not an optical photon, it's not an X-ray photon. So it's out in the radio, so you need a radio telescope to observe this thing. And the other effect, you have the redshift effect, so it's even at a longer wavelength.
Right.
Unless the hydrogen gas is really nearby, so there's no redshift effect to worry about. So that's why you need a radio telescope to see it. So you're not looking at molecular hydrogen, two hydrogen atoms bonded together to form a molecule. You're looking at single hydrogen atoms that have all of their electrons, which means one. There's one proton and therefore one electron to make it a neutral atomic hydrogen atom. So that's how it works. Now, molecular hydrogen is much more difficult to detect in astronomy.
Yes.
In fact, there are some lines, spectral lines in the ultraviolet and the infrared that we can use, and most of them are observable best if you're above the Earth's atmosphere, so space-based telescope.
Right.
But from the ground, what you can do is a trick. You can use carbon monoxide, CO, as a tracer gas for molecular hydrogen. And it's almost like, I like to use the example in my astronomy class when you have like propane for your barbecue.
Mm-hmm.
If you took natural propane,
It's colorless and odorless.
Yeah, it's odorless. You can't smell it. Yes, yet propane for your barbecue has a distinctive odor. Why? Because they put something in the propane to give it an odor so that you can more easily detect any leaks.
Right.
So it's a safety precaution. So it's kind of like that. The carbon monoxide, which we can detect easily from the ground, acts as a tracer. So when you find carbon monoxide, you can infer that in the same general area there is molecular hydrogen. You just have to know what that conversion factor is, and you can estimate that by directly observing molecular hydrogen and comparing to the abundance of carbon monoxide that you get, and then assume, here's an assumption, assume that that is the same value you get for the whole galaxy. In fact, you can measure it for other galaxies carefully and see what the difference is, or make an assumption about all galaxies that this would be the conversion factor. So that factor probably varies from environment to environment, but at least you have an estimate of the molecular hydrogen that's out there. You have a starting point. So so what you're seeing here, these galaxies are being disturbed because of their infall into the galaxy cluster environment. And the other thing to notice is nothing in space is closed box, as we say in physics. And closed box means totally isolated from any external effects.
Right.
And why would you make that distinction? Well, it turns out that when you model different things, different processes, different phenomena, you can model them more easily, usually, if you assume a closed box situation. You don't have to worry about anything outside of the object you're looking at, outside of influence.
Coming in or moving out. Yeah.
And it makes life a lot easier. But as we discover, and you can do that as the sort of the first stage in your analysis process, and then the second stage is the closed box scenario actually valid or not? And in most cases it is not valid. Then you open it up a little bit and say, okay, if it's not valid, what things do I need to change in my computer simulation, if you're doing that, to make it more consistent with reality, an open box situation where you have an inflow of material from the outside, for example, or you have some kind of influence with magnetic fields. You could think of a number of things, right? Gravitational effects from objects nearby and all these sort of things. So galaxy clusters are clearly open box, right? There are lots of things that are flowing into the clusters and so on that you have to be aware of, and this is part of that process. Now, Robert, the next story to look at involves the detection of gravitational waves.
Okay.
Now, the first experiment that was built to detect gravitational waves, which we succeeded back in September the 15th, I believe it was, of 2015, was the LIGO experiment, which stands for Laser Interferometer Gravitational Wave Observatory. And there were actually two facilities at the time, one in Louisiana, which is close to home for you, and one up in Washington State. And the reason why you want to have that is because you can do some amount of triangulation. If you observe gravitational waves, number one, you know it's not a false positive because both detectors would go off in the right way and measure the same waveform.
Right.
And the other thing is, with two stations, you can isolate which way did the gravitational waves go in terms of their path. Did they come from this side of the Earth, or did they come from the other side of the Earth? And having two will help that.
Right.
Since that time, of course, the number of gravitational waves observatory on the Earth has expanded. So we have the Virgo that goes with it in Europe, and we have the Japanese station, the Kagra.
Kagra.
So now we have three of them. And they release their data to the public, so it's not like it's hidden. Every once in a while, there'll be a data dump, and people can go online and download the catalogs of all the gravitational wave detections and so on, and analyze it. Some people, for example, have developed really sophisticated algorithms, AI-based probably, I would assume, deep learning, machine learning algorithms that would process the data a little better than what has been published and come up with some of these weaker gravitational sources.
Okay.
to try to expand the catalog as much as possible. And in case you haven't listened to our podcasts in the past where we talked at length about gravitational waves, so these can be viewed as undulations in the fabric of space-time due to accelerating masses. So think of, for example, two black holes that are orbiting around each other. They will release gravitational waves which will vibrate in some sense or cause oscillation in space itself. They're usually very small, very low amplitude type of oscillations until the black holes get really close to each other and they lose energy through the emission of gravitational waves. So they get closer and closer, they in-spiral, as we say, and eventually they can merge. And at the point of merging, they release a burst of gravitational wave, and solar masses of material are converted into energy of the gravitational waves. So
That's
we always
crazy.
like to say that space is extremely stiff. It takes a lot of energy to make it move, if you like.
Right. Now,
So
I'm going to interrupt you to
Yeah.
ask a question here because I'm being a little ignorant. With those three, and LIGO having actually two detectors, that gives you four.
Yes.
Does that mean we can expect some gravitational wave images because you've got closure phase?
Well, I mean, what you would have is the waveforms is what we detect.
Okay.
So we don't have imaging, as in the sense of cameras.
Okay. And that's what I was
Yeah.
asking. Is like with radio telescopes, you get 3 or 4 of them. You can close the phase and get all the phase angle information and make a picture
Yeah,
from it.
what you can do is get much more precise information about the location.
Right.
Think of right ascension and declination on the sky, location of where these sources come from. In fact, we know one source, exactly where it comes from, because it was a merger of a neutron star with another neutron star and a neutron star with black holes we've detected also. And in
Okay.
this event, people had a general idea where it was coming from, and they trained telescopes to survey the area, and we found an electromagnetic signature, a burst of light coming from a certain part of a particular galaxy due to the merging of these objects, neutron
Nice.
stars.
And
So, and that,
Yeah.
you can take an image of that because there was the light signature that comes from it. If you have just two black holes that are totally isolated, which means they don't have any material that's in orbit around them, what we call naked black holes, when they merge, there is no electromagnetic signature that gets released, no forms of
Right.
light at all. In fact, you wouldn't even know the event occurred if you were using ordinary telescopes, regardless of the wavelength you're observing at, because it would not release light.
Right.
And the only way we can tell that this happened, this event, is through the emission of gravitational waves.
which is pretty cool in and of itself.
So that's
Yeah.
why we say that with the use of LIGO and others, that this opens up a new window in the study of astronomy, the study of astronomical objects.
Yeah.
So the interesting thing is you can download the data and you can analyze it, like I said, on your own. And what someone has done here is that they've taken the LIGO data and actually looked at what is the change in the sensitivity of the detection of gravitational waves. What does it depend on, if there is a dependence? So they actually mapped out the dependence of, for example, the day of the week in which the gravitational wave is detected, whether or not it was on a weekend, for example, whether or not it was in the evening at the location of the observatory, or maybe in the daytime when everybody's sort of around and busy. They even detected variations due to the change in the daylight savings time
That's
when our
crazy.
clocks go ahead. These kind of things. And a lot of it is due to earthly considerations. That's
Right.
what's going on here.
You've
right?
got more
Humans.
noise at a certain time. and-
Yeah.
Yeah.
And for example, maintenance was done on a Tuesday. So after the maintenance is done to the observatory, the detectors are more sensitive for a while.
And that makes sense. And they're not as sensitive while the maintenance is going on.
Yeah, and then or many days after the maintenance cycle, just before you're ready to do it again, like let's say on a Monday, then the sensitivity is not as great as it would be on the Tuesday after the
Yep.
maintenance was performed. So you have all these earthly kind of factors that you actually can get from the data itself. It's amazing when you think about it.
It is. But, this is why, I keep trying to point out to people that we have reasons for saying what we say. So how do we know it was a gravitational wave detection and not a truck passing by? And the answer is one, it's detected the same wave in 2 different locations. But number 2 is we take into account all this type of stuff. that maintenance is being done on certain days, that this is happening on certain days, and you can filter for all those effects.
And they even put in false detection to keep everybody on their toes. So it's called, the ejection of these false detections depends on, they get injected into the data stream at certain times. And so you can actually pick out that as well.
Yeah.
Because there are times when people are sleeping too, right? And all
Right.
this kind of thing. So it's quite interesting. You can detect all these kind of earthly type things, human activity, when you're looking at gravitational wave sources, billions of light years away.
Right.
It's amazing when you think about it.
Absolutely. Okay. There we
Now,
go.
the other thing that's been in the news lately is the release of the largest cosmological simulation to this point, or to this time, if you like. Now, this simulation, which is known as the Euclid Flagship simulation, is in support of Euclid, which is the mission to observe, large areas of the sky, looking for, help track dark energy and dark matter and all this kind of stuff. And you want to build a simulation to kind of compare it to the real observations to see if that tells you something interesting about the universe itself.
Right.
Now, this simulation is an n-body simulation. So you know what an n-body simulation is, Robert?
That just means you have a lot of particles and you're putting in the physical laws of nature, gravity, electromagnetism, etc., and running it to see what comes out.
Yeah, let them interact. In fact, you could think of, what's a good way? Let's say you could simulate a jar full of gas molecules, and you inject all of the gas molecules, it could be, let's say, 100, and you'll have them in one corner of the container, and then allow them to undergo their physical interactions that they would do, and see how long it takes the system to come down to a dynamical equilibrium. How many
Right.
seconds does that take?
Probably 100 particles, probably not even a second,
So you can use that and then scale that to get closer and closer to the true value,
Right.
the true kind of reality, if you like, to the real modeling, to mimic Mother Nature. So you can do all these kind of things with these type of particles. Now, the more particles you have, the more memory you need in your computer. So this is not something you can run
and the
on
more
a
CPU time.
and the more CPU as well. So you're talking about multiple nodes, parallel processing, terabytes of RAM, all this kind of stuff. And this,
With that many, probably petabytes.
yeah, so this simulation in particular uses 4 trillion particles. If you go back at the early simulations, they used a dozen or so, right?
Right.
So, and it's all because of the advancement of
The
technology.
computers, the
There's been
technology.
advancement in algorithms, sure, but it's really the advancement in processing power and memory and technology, right? Computer technology. So 4 trillion particles. That gives you a cube that's like 16,000 by 16,000 by 16,000 particles in a volume of space. Now, you might say, well, that is fantastic. Can you model like everything? No. The individual particle has a mass of 10 to the 9 solar mass.
That's
Now-
big. That's a galaxy.
Well, there's a lot more things you need to model, right?
Yeah.
This 10 to the 9. There are a lot more objects out there that have mass less than 10 to the 9.
Right.
We're talking like individual stars, which have about 10 to the 1, type of thing. So you have to come down, 8 orders of magnitude to get down to that 10 to the 1 type of thing. And so you need a lot more than 4 trillion particles. So these are going to computers that will be invented, hopefully, in the far distant future. We'll have them to be able
Yeah.
to model everything right down to the massive stars this size of a volume of space. But that's going to take a lot of computing power.
Oh, yeah.
So we'll see how that plays out. But with this simulation, you can, in this case, it was 3.4 billion galaxies. So out of those 4 trillion particles, 3.4 billion galaxies. And another cool thing is for every galaxy, they modeled 400 different properties, like brightness and different filters and so on and so forth.
Oh, wow. Okay.
Yeah, so it's quite interesting. So, I mean, there's lots of stuff you can do with this, obviously, and it's released. Like anybody can look at it and download it and have fun with that because it takes a lot of
You're going to be downloading for a while.
it's a lot of data to and then you got to process it. Like, what's the algorithm? And you want to be able to sift through this data rapidly. You don't want your algorithm to take like 5 years to give you the answer.
Right. But that's
You know
probably
what
exactly
would
where you're
happen,
at.
right? You know what would happen?
Your computer would die before.
No, well, the computer would run for like 4.99 years, and then just before it spits out the result, the power went down.
True.
And your UPS failed. That's what
True.
happens, right? Now, here's an interesting story. Robert sighs on this one, and I'll just read the sort of heading. So this was a meeting that took place this summer in Helsinki, Finland, and it's looking at then the effect of how rare is technologically advanced extraterrestrials.
Mm-hmm.
And in particular, this study then looked at the conditions that you need, plate tectonics, and actually some level of carbon dioxide to support life as we know it. And if you have no plate tectonics and too little carbon dioxide, that's actually a major influence on the, if you like, the how popular, how common is alien life at the technological level. We're not talking about bacteria or anything like that. We're talking about advanced alien life. And they estimate that the nearest advanced civilization in our Milky Way is on the average probably about 33,000 light years away.
Yeah, but that still means there's hundreds of us.
Yeah, in our galaxy, that's right. But the nearest one is 33,000 light years away. So I Love Lucy has gone out to about 100 years or roughly on average, rounded up. Yeah, it's not even close of going out 33,000 light years.
And by the time it reached 33,000 lights, Lucy is background noise.
Right, because it gets weaker and weaker with distance.
Yeah.
So, go ahead.
The reason I sigh is because I've seen lots of discussion and about the importance of plate tectonics. And while I agree for our type of life on this planet, it's important because tectonics is how you get a carbon cycle going. You know, so that's how you recycle carbon dioxide, carbon through the crust in the atmosphere and back into the crust. And without that, a lot of our bacteria and plants, things like that, don't grow as well as they should. But again, we've got a sample size of 1. And so, yeah, I'm just dubious of any such claims because of that.
And you can see the calculation here. So here's a graph on the vertical axis. We have the estimated maximum number of advanced extraterrestrials. And on the horizontal axis is their lifetime in years. And so in the graph, you can see the different lines that's plotted there and the different fraction of carbon dioxide, sort of the nominal case, the maximum case, the minimum case for 10%, and then 1 for 1%. And you can see how the numbers for the 1% is below for the 10% version of the model. And that just showing you that there is less of a chance of extraterrestrial intelligent life when the carbon dioxide values are that low.
Right.
That you need that as conducive for life as we know it.
As we know it.
But a caveat's always got to be there.
Because, who says photosynthesis took hold? Well, that's why you need carbon dioxide is photosynthesis. If photosynthesis, some other type of energy conversion system set up, you wouldn't need the CO2. So who cares?
Right. So this is, planets with nitrogen-rich atmospheres, and then you're just altering the value of the carbon dioxide percentage in that. But it's interesting also to note the lifetime here. So they mentioned the fact that you're talking civilization must be at least 280,000 years old or up to several million years old in order to catch it now, today.
Right. But again, there's a lot of caveats on that because, we're going radio quiet. Have we wiped ourselves out? Well, that's debatable. But, we're no longer broadcasting omnidirectionally. Our broadcasts are now directional towards the receiver. We're using fiber optics. We're going radio quiet as if we've been wiped out. So we lasted 100 years as a radio transmitting species. So again, is that a normal progression? Anyway, yeah. I like the mental spitballing and speculation that goes into these types of discussions and studies. But in the end, you've got to make sure you say that's what it is. It's speculation. It's spitballing. It's playing around with the numbers and saying, well, what happens if this is the case?
Well, it's interesting to think of if you wanted to remain quiet as a civilization because you're afraid of the Borg.
Right.
Or equivalent. Then how would you do that? So you wouldn't allow powerful transmissions out, that would take place on your home planet. And you can't hide the fact that you live on a planet around some star, that star has a system of planets, a solar system.
Right.
Because anyone with sophisticated enough equipment can detect planets around your host star.
Right.
And that would be through different methods, like the transiting method or the radial velocity method.
And even if you had a Dyson sphere that hid the star from view, Dyson sphere, by the way, is a sphere that's built around the star itself. So even if you had such a thing, you would have to dissipate waste heat. And so your Dyson sphere would glow like a star in infrared.
Yeah, in fact, there have been several researchers that have taken data from the WISE spacecraft, which was a NASA space telescope that re-entered about a year ago. But it did a all-sky survey at infrared wavelengths and released that data for everyone to use. People have searched through those catalogs looking for unusual infrared sources to see if they could be a signature of a Dyson sphere.
Right. And again, great idea. I love it. But, this is almost more science fiction than it is science.
Yeah. So it's hard to hide yourself.
It is.
In a way. But it's certainly you can make yourself extremely quiet.
Right.
By having everything going through optical fibers and so on and so forth, the transmissions, and not broadcasting, heavy-duty military radar out beyond, or purposely broadcasting signals, which we've done in the past also.
Was it Stephen Hawking who was the one
who
Stephen advocated against broadcasting?
Yeah, he said, if you're in the jungle, it's probably safe not to shout.
Right. I was wondering if it was him.
Yeah, so Stephen Hawking was the one that was supporting that idea. Others would say, well, if you're out in the jungle, the only ones who are really going to hear you are sophisticated, statistically wise, well beyond us, and way more advanced, and therefore have gone through a stage in their development where they realize that maybe it's not a good thing to wipe each other out or destroy the planet that they live on. That's the idea, more of a utopian type of situation, that they would not, wipe us out if they knew that we existed in some location of the galaxy.
And I'm like, how well has that worked out on our planet?
Yeah. In fact, if you had a lot of power, and I mean a lot of power, like so much so that you are able to explore the galaxy fairly easily, I would assume it would only take like a blink of an eye to destroy the Earth completely, and we wouldn't even know what happened. It'd be so quick.
Right.
We just wouldn't be here.
At
some point.
I'm going to be one to argue in the favor of Babylon 5 race called the Mumbari. Babylon 5 is a science fiction show. And their greeting is to throw open the gun ports and show, hey, we've got nothing to hide. This is our weaponry. So to a degree, I have to wonder how much more sense it would actually make to just blast power so that you could say, yeah, I'm here. Come at me, bro.
Okay. And with that, we don't want to get Robert too agitated.
Yeah. No,
you're true. Lucky you're not near him. I'm right beside him. No, I'm only kidding.
Hey.
Only kidding. Now, the other thing I want to make sure we cover today is, once again,
radio telescopes.
No, interference by satellites, right? So this has been a big discussion ever since Starlink and others are putting up all of these satellites in low Earth orbit, that they're causing problems for astronomers. For optical astronomers, you get all these multiple streaks across your images, and so it's hard to process those away. In fact, large telescopes that are just coming on now, like the Vera Rubin Observatory down in Chile, and this has been a major problem because it looks at a wide area of the sky in every single exposure. So the odds of a satellite trail being in a single exposure is quite high.
Actually, the odds of several satellite trails being
quite
in
high.
Exposure.
So that's really going to have an effect on the processing that you need to do to remove that influence. And then to get around it, some people would suggest, well, just put your telescopes in space. Yeah, but that costs money, a lot of money. Where are you going to get the money from? It's easy to say, put your telescope in space if you don't have to cough up the money for it.
Right.
That's the problem.
And then I'm going to go, how are you going to get a 30-meter telescope in space?
You stuff it in the rocket tube, like an umbrella. And then when you get it up there, it pops open, pop. And of course, you can't hear it pop because you're in the vacuum of space. And in space, nobody can hear you scream. Why
Right.
would you be screaming? Because all the money you spent getting your stuff up there to begin with.
Right.
Now, that's the thing, right? It costs a lot of money to put telescopes in space. We can't afford. In fact, people have problems getting money from the government now to do research and science. Imagine you go to and you want all this money to put telescopes in space. That's an issue. But it's not just optical astronomers that have to worry about this. Radio astronomers have to worry about this. In fact, this has been on for decades now. I remember back in the Iridium satellite days when people were putting up Iridium satellites that we worried about the interference of the radio signals that they're transmitting, communicating with, that they bleed off into neighboring wavelengths.
Right.
That they're not all confined to some narrow band or something, and you just got to avoid that band. That's not the case. You get bleeding. So there are protected frequencies that we have on the dial, if you like, where radio astronomers are allowed to use those frequencies to monitor astronomical sources, like we talked about already today, that 21.1 centimeter wavelength.
Right.
Those frequencies are supposed to be clear. Nobody is allowed to broadcast on those frequencies unless it's an emergency. I think you're allowed. But other than that, you're not allowed. But we do see radio interference leaking into those bands because electronic equipment is not perfect. Plus, you have the different harmonics involved, and you got to have very sophisticated filtering systems geared up so to stop that type of radio frequency interference. So it's a hard thing. But once you have very sensitive radio telescopes, which we've had for quite a while, like Arecibo, and so on. Now the FAST telescope in China, which is the one you see there on the far right, that's 500 meters in diameter. It's a very sensitive radio telescope. It's going to pick up a lot of this interference, or it can, and that causes a lot of issues with processing the data. You don't want to be influenced by earthly things if you're trying to look at astronomical objects.
Right. I mean, I don't want to be influenced by earthly things. So.
Well, how do you minimize this? What's the big thing that people are getting into now? Finally, it seems like there's more emphasis on it in terms of radio astronomy.
I'm not really sure what you can do about it.
Well, you put your antenna on the backside of the moon.
Oh, right.
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 So
That's
you
what
use
people are talking
right.
about.
So you use the moon as a natural shield. I mean, Jack Burns is a radio astronomer who's been pushing this a lot.
There's now starting to be a lot of satellites orbiting the moon.
And that's the problem, right? Is what happens is, like China, for example, had a rover on the far side of the moon for the first time ever. But how do you communicate the rover with the Earth? The moon's in the way. You have a satellite in orbit around the moon that relays the signal back to Earth. But of course, that's broadcasting on radio frequencies. So now, if you had a big, huge dish, radio dish on the backside of the moon, that radio dish may pick up the interference from that satellite communication. And of course, this is probably becoming more popular as we go forward in time, more things happening on the moon, including on the backside of the moon, that we're going to have a lot more of these satellites in orbit around the moon. Think of the Lunar Gateway, remember? That's a part of the Artemis project. That's supposed to go in orbit around the moon. Whether or not it gets fully funded or who knows. But, if that doesn't get funded, other things will. So over time, even the backside of the moon will be contaminated.
Right.
And then what do?
I go to Pluto.
So it's sort of a never-ending situation here.
Right.
It's going to get worse over time anyway. So
And it's time to start talking about it and trying to do something about it. And people.
Or just look at light pollution.
Right.
Right. I mean,
Lord,
what was it? 80% of the human beings on the Earth are living in a location where they can never see the Milky Way galaxy.
Right.
80%.
Yeah.
And unless you journey away from your house, that is, go on a camping trip or go on vacation somewhere, you'll never see the Milky Way.
I mean, Grand Forks is not that big a town, folks, and you've got to go 10 miles outside of town before you can see the Milky Way.
Yeah, the light pollution is amazing. Even on campus here, we had a public event last night where we used a telescope to look at the moon and Saturn and so on, and the lights are unreal. And in fact, I noticed there's a safety event coming up in October where you walk around campus at 7:30 at night and looking at safety considerations like poor lighting. So the result of that could be the installation of even more lights on campus.
And there's too many as it is.
It's a never-ending type of thing, right?
Right.
So, I mean, if you look at a map or an image of the United States taken at night, it's all lights all the way from the East Coast right to the Mississippi.
Right.
And then you see a reduction in the light until you get to the major cities, of course, you see
But I
all
will
lights.
note that it's a reduction in the light. It's still not dark.
Still not dark. And
anywhere.
eventually you get to the west coast and it's full of lights again.
Right.
And the dark part is really in the mountains area, right?
Mm-hmm.
That's less populated and less of the city lights. But why do lights need to be pointed straight up? How does that help anybody?
Right. Put hoods over them. That would help with some. at
Yeah,
least.
put proper shading on your lights. You got to have light on campus for safety. I can understand that, but use proper shading. Don't
Right.
allow the light to go up in the sky. How's that helping anybody?
And use motion detectors so they go out when nobody is there.
Yeah, but essentially, we're as a society. It's not just UND. It's everybody. As every country, as a society, we're ruining the night sky for
Right.
people to view.
Because people just don't feel it's important. And I don't understand that.
And it's becoming more and more difficult for telescopes to find a place to be where they can observe in dark sites.
Right.
And you might think, oh, that won't impact me. Well, thinking about impacts, what happens? It was the light pollution that prevented us from detecting an asteroid that was inbound to the Earth that got gravitationally perturbed from its normal orbit. So it was on a different orbit that was Earth impacting orbit that wiped out everybody on the Earth because of light pollution. We ultimately couldn't get up there in time to do something about it.
Right. Because it had to be too close to be bright enough for us to see.
Yeah.
And as Wondergoon says, make better humans.
Well,
That's the hope, but
AI will do that.
define better. I agree though, but you know what I'm saying.
Yeah. Anyways, so moving on.
Moving on.
So speaking about radio, here's an interesting object that a paper just recently published earlier this month. It's about an Einstein cross.
Okay,
Now,
I've
if
heard
you-
of Einstein rings, but I've never heard of an Einstein cross.
So Einstein cross it's related to the Einstein ring, which is a ring of light that's due to the alignment, the just perfect alignment of a background light source with a foreground object. That foreground object has curved space in its vicinity due to the presence of its mass. And it's curved it in such a way that the light coming from the background object then passes through the vicinity of the foreground object, and that light gets altered. Its path gets changed. Think of light passing through glass, how that alters the path of a light ray, for example. And it does it in such a way, if the alignment is perfect, to make this nice, beautiful, bright ring. And if you're interested in that type of effect, just take a champagne glass and tip it over so it's like horizontal. But of course, drink the champagne first. Don't want to can't waste good champagne. The $2 bottles that I buy.
Right.
Anyways, so you tip the glass horizontally, then lift it up and look through the glass towards the base at a bright light source. And if you move that glass in front of the light source, you'll see this nice ring at the stem of the glass. And that's essentially what's happening with these Einstein rings. Now, in this case, what you get, instead of the perfect ring, if the alignment is such, you'll get multiple images of the same object. And that's the Einstein cross. So if the alignment is right, you typically get 4 images of the object.
Okay.
In this case, we're getting 5.
That's neat.
So it makes it a little bit more unusual. Now, the image you see on the right, that's taken from ALMA, the Atacama Large Millimeter Submillimeter Array, that's down in the Andes Mountains, in the Atacama Desert in Chile. And it's really high altitude, so high, in fact, it's very difficult to breathe. Robert, you'd be the perfect person not to send to that location.
Absolutely, yeah.
In fact, the people who get around good without an oxygen tank strapped to them are people from the local area because their bodies, have built in a sensitivity to the oxygen levels and can perform well compared to somebody who lives at sea level all the time.
Basically because any children born like I was don't survive at that altitude. So
Yeah.
I hate splitting it that way.
Or you have to move fast.
Or you have to move fast.
So with ALMA, which is observing at the radio wavelengths, in fact, this image is taken at 292 gigahertz. It's a continuum image, which means you're not just looking at emission lines.
Okay.
You're looking like between the spectral lines, the actual continuum itself. And you can see evidence then for this Einstein cross. Now,
Neat.
the object that you're seeing imaged here is about 11.5 billion light years away. And the object that's responsible, the foreground object for the lensing, create the lens, is about 7.8 billion light years away. It's at a redshift of 1, where the object that's being lensed, the background object is at a redshift of about 3. For those of you who are into redshift numbers,
Right.
there you go. So it's kind of cool when you think of this. So this is a really neat image of it. And in fact, if you go to the next slide, this is actually a combined Hubble Space Telescope image taken in the 110 filter. So this is in the infrared, 1.1 microns essentially. And situated on top of that is an image taken at 1.2 millimeters. And this would tell you or signify dust, so emission from dust, right?
Right.
So it's light coming from heated dust essentially. And it's also a continuum map, so it's not specific spectral lines. To astronomers, that's important to know what that is. And this image is, or this, if you like, a mapping of the continuum from dust is taken by a radio telescope array in Europe called NOAMA. So NOAMA then produces a relatively new radio telescope array, produced this image. So it's a 1.2 millimeter map then and overlaid with the HST images to better constrain. And you can see the objects here that are responsible then.
The foreground objects.
Yeah,
Anyway.
so they're labeled G1, G2, G3, and G4. Those are the objects in the foreground that are responsible
and
to do the
now I
lensing.
can see why it produced those 4 images of the background galaxy.
Yeah, so you can see the contours, right, of the part of the Einstein cross. You got 3 sort of near G1 and G3. You have 3 of them in a line, and then you got 1 to the upper left and 1 in the lower right to give you your 5 altogether
Yeah.
to make up the Einstein cross in this situation. So it's pretty funky. It's not unusual, to have those lensing stuff. In fact, when people first thought about these lensing that we talked about already, that actually occurred to Albert Einstein way back, even before the publication of his general theory of relativity. Einstein had done a calculation about the probability of lensing and what it would be like, what would be the distance you need, the alignment and such to get this sort of effect that occur. And you can even write down an expression for magnification and so on. And that's what you see on the left side here. So this is an image, a reproduction, if you like, from the collected papers of Albert Einstein, which is owned by Princeton University Press.
Which was his last place of employment. If I
Right,
remember.
yes. And you can see the calculation, which is kind of the standard calculation we use now when we describe the alignment effect and the lensing phenomena. And he published this in April, or wrote this down in April of 1912. And like I said, this is like, a little over 3 years from the publication of the general theory of relativity.
So he was working on general relativity for 3 years.
Yes,
at least.
for multiple years.
Yeah.
He essentially worked on it for like 10 years.
Okay.
So after the special theory of relativity was done in 1905, he started working on the general theory. Now let's bring gravity into it and make it a more general theory. And by bringing in, and it took about 10 years to get the math sorted out. In fact, he had to go to his friend, mathematician,
Yeah.
to figure this out. And other mathematicians at the time had pretty well stumbled on the general theory of relativity, but based on Einstein's talks that he would give along the way. So he'd give updates on what he was thinking and what was going on. But
Okay.
Einstein was the one that kind of put it all together, so he gets full credit. It was his idea anyways, he gets
Right,
full credit.
right.
He could have been scooped, but he wasn't. People back then were...
Had a little more
Integrity.
Yeah.
Yeah. Anyways, so and the other interesting thing is the paper that was published in Science, and this was many years later. This is in 1936. This is the panel you see on the right, and it's interesting when you look at that. He actually published a calculation that describes gravitational lensing, sort of what he did back in 1912. He did it in 1936 and actually got it published. And I'm going to use that as a quote for the end of the podcast, so I'll save that discussion here in a few minutes. But it's just one more of those things, right? What was the other thing that you discovered recently that Einstein had wrote a paper on? You remember? I mentioned it to you one day and you looked it up and you said, "Oh, I didn't know that he was involved in that type of device."
I don't remember.
Where
Sorry.
do you put your leftover?
Oh, refrigerator.
Yes.
Yes, he did essentially a chemical refrigerator instead of a electric or thermal gas refrigerator. You needed a heat source, but it could be an open flame to heat up a mixture of ammonia and water and it would get a cycle going that would cool things without a compressor.
Right. So Einstein was involved in a lot of stuff. You can
Yeah.
actually do a search on all the papers right on the internet and see what articles that he was either the first author or a co-author on. It's
Yeah.
amazing when you look at it. In
It
fact,
really is.
you think of the miracle year, 1905, right? He was involved in the special theory of relativity. He was involved in a paper describing Brownian motions. You remember what that is?
Yep.
So what's Brownian motion for those who don't know?
Brownian motion is essentially the impact, the visible impact of molecules moving in a substance, a fluid, on small particles like grains of pollen or something like that. You can actually see them jiggling around from it.
Have you ever observed that
I have.
in a high-powered microscope?
Yes.
Interesting. Do we have that equipment here, Robert?
Yes, we do.
We should put that together and see if we can see that.
Our laser tweezer experiment
Right?
that's upstairs. We can actually you can actually see the Brownian motion.
Oh, nice. Beautiful.
So,
By just trying to reproduce what they would have saw in the 1800s or early
Yeah.
1900s with the microscope.
it was one of the first confirming pieces of evidence of the atomic theory.
Yeah. And so Einstein publishes a paper on that in 1905, and the other paper was the photoelectric effect.
I remember that paper because that one's neat too.
Yeah, so that's we all know what that is, even though we may not know the term, and that's use of
That's the photons falling on certain materials will knock free electrons, producing then a current. In other words, a photovoltaic solar cell.
a solar cell, like you might have a solar calculator.
Right.
That's how that works. Or you think of doors opening, right, from light that goes from beam of light from one side to the other, and you cut that beam, and it does something like open the door because something's there or whatever, right? There's all
Right.
kinds of different things nowadays that we use that for. So yeah, Einstein described that what was going on from a theoretical point of view. In fact, he got the Nobel Prize in Physics for that explanation.
Right.
So which is kind of funny because you think Einstein, you immediately think of special relativity. Nothing goes faster than the speed of light in a vacuum of space. E equals mc squared type of stuff, right?
Yep.
Or you think of the general theory of relativity. Light gets bent when it passes near the sun. You can observe that during a solar eclipse, right? Or time slowing down as you travel really fast from special relativity.
What
All
he
of-
won the Nobel Prize for was photoelectric effect.
Solar sails.
Solar cells. Yeah.
And you might wonder, why is that the case? Well, it took a while to confirm a lot of these, at the time, far-out ideas like special and general relativity. Mm-hmm. And so SR and GR, and it took many experiments and many decades before people got
started
convinced.
going, okay, this
Yeah,
may be right.
this works, right?
Right. Because a lot of people didn't like it. I mean, it brings about some really strange things like bending space.
Or the altering of time depending
Or
on
the
your
altering of
motion.
time. Right.
That's the other weird thing. All kinds of things. And that there's this limit, this fundamental limit that a material object, anything with mass, cannot travel faster than the speed of light. We can't accelerate to go faster than light speed. So there's this fundamental, and it's not like the speed of sound, where that was an engineering hurdle that we ultimately broke, obviously.
This is part of the very fabric of space-time. It's baked in to the nature of the universe.
Yeah, and it gives rise to that funny cartoon that you see sometimes where you see a rocket that just landed on the Earth, and there's a ramp coming down from the hatch,
Right.
and there's these young people, strolling down the ramp, and waiting for them is a guy that's bent over with a long beard and a cane in one hand, and then a female who's in a wheelchair, and they're side by side. And they yell out to the people coming down the rocket, all spry, "Mom and Dad, you're back." And you're like, how the heck could your parents be like in their 20s and you, the children, the siblings, are like ready to die? You're like in your 80s or 90s. And that's because the parents went in a rocket ship and traveled very close to the speed of light for a period of time. Time for them slowed down to the point that by the time they got back to Earth, maybe only a couple of years went by. But on Earth, maybe 60 years went by or 70 years, depending.
Yeah.
And so your children are now really old, ready to die in the next few years, and you're still young and spry and running around.
Yep. And
that's not science fiction. That's science fact.
yep. I mean, we've measured it. Your GPS works because we had to measure it and take it into account. So, these are not speculative things that have not been actually proven. Yes, they have.
Yes, they have. And yeah, as you mentioned, the GPS would not work and didn't work when they
until
first
took
brought it
into
online
account.
because they didn't account for relativity, both special
And general.
and general. Why general? Because the satellites are in orbit of the Earth. They're further away from the Earth itself. So space-time is warped less around the vicinity of those satellites than it is for a ground station on the surface of the Earth.
So the clock ticked at a different rate.
It ticks at a different rate. And the other thing for special relativity is the clocks on the satellites are moving.
Right.
And because they're moving, there's time dilation. They'll click at a slower rate compared to a clock that's not moving.
Yep.
So you
And
have to
This
account
amounts
for
to
that.
nanoseconds of a difference. But over time, that nanosecond drift makes your positioning information drift.
Yeah, it accumulates.
It accumulates.
So, using the military aspect of GPS, which was obviously what it was invented for initially,
right.
instead of putting a missile through a window of a house on the other side of the world, you hit a different city altogether.
Right.
Or so it's useless, that system, if you didn't compensate for the relativistic effects. So it's amazing when you think about it. So if you want to live longer, Robert, go very fast.
Go very fast. Live fast.
So I want you to run to your car after we're done this podcast on your way home to the parking lot. Run as fast as you can. Actually, that might shorten your life. You might die of a heart attack or something.
Right.
Maybe you shouldn't do that.
I was about to say, lengthen it by a few attoseconds and shorten it by a few hours.
Well, imagine people in the International Space Station.
Yeah.
When they're up there, right? They're going to live a different life if they didn't go up there, but that difference is minute.
Is microseconds.
You could probably smoke one cigarette, one dart, and then that wipes out any gain you had by going on the space station. Statistically, right?
All right.
Yeah.
Yay.
So if you're interested in these type of ideas like relativity and learning all about it, and about time and its
warpage
non-absolute nature, its flexibility, how it clicks away at different rates depending on the person that has the timepiece, for example.
Yeah.
Then come to the University of North Dakota and take some courses, you betcha.
You betcha.
In science and STEM fields and arts, and describe things what you see and try to explain these things to other people. That's why we need lots of writers. So English majors, like somebody we might know, Robert.
Are just,
all of these things.
Are even writing the science fiction that we've been talking about, because that is inspiring.
Yes.
It makes people get interested in these sorts of things. So join us, no matter what you feel.
That's why we have a space program, to get people motivated.
To get people
besides
motivated,
learning
interested.
about the wonderful things that are around us.
All right.
Now, we always leave you with a quote at the end. And before I say that, I should note that our next podcast will be a week from today. So that's October the 7th. In October?
Into October.
In October already. So this quote is, as I had mentioned or alluded to earlier, is from Albert Einstein. It's from the paper that he published, this excerpt from it, in the Science back in 1936, the Journal of Science. So this, if you want to look up the reference, it's volume 84 and page 506.
Nice.
Published in the year 1936, just before the Second World War got going. And here's what he said. Some time ago, R.W. Mandel paid me a visit and asked me to publish the results of a little calculation. Modesty is everything, right? Yeah. Which I had made at his request. This note complies with his wish.
Nice.
And that was the main calculation that he had done, as we mentioned already, way back in 1912.
Because
he
people
finally
were interested.
Published it. And I think back then, just to kind of aside here, because the alignment has to be nearly perfect, that the prevailing wisdom was that the odds of that happening is so small that you probably will not see this effect. I know other astronomers like Fred Zwicky and others has suggested that should be there, but the odds of you finding it is pretty low.
And
so
we didn't for a very long time.
We didn't for a very long time.
And I think it was Hubble actually that started showing these things on a regular basis.
On a regular basis, but they knew before that, ground-based telescope. In fact, I think the first Einstein cross with 4 images was actually discovered back in the 1970s from ground-based telescope at that time. But yeah, it took a long time, but finally with the right instrumentation, something that you would think that it would be very rare actually becomes quite commonplace.
Yep.
Very interesting.
Indeed.
Now, if you like this podcast, please don't forget to give us a thumbs up. Smash that like button. Tell all your friends about us. Come join us.
Come join us.
If you have questions or comments you'd like to make throughout the podcast, please do so. So if you listen to us afterwards, we broadcast live every Tuesday at 5 o'clock Central Time.
Yep. Because it's almost time to flip back.
That's why I said it that way. And if you haven't subscribed, please subscribe.
Yes.
That lets us know that people are interested. If nobody watches this show, it will go away because what's the point, right?
What's the point?
It'd just be Robert and I talking like we used to without
and we can do that
everything.
on our own.
Then we can curse, right? Just kidding. Anyways, thank you very much for watching, and we will see you next time.
All right. Bye, folks.